excellent. Yeah. So today, yeah, we're very happy to have Miao to give a talk for us on his recent and a very interesting work on the European aluminum 4. I really know Miao, I mean, for many years when he was a graduate student actually with Han, right? Yeah, we never worked together, but I know his work. He has been fantastic and working also quite a bit the Brookhaven National Lab before he actually moved to Oak Ridge, become a staff scientist at Oak Ridge. Yeah, so he's been extremely productive. So today we're very happy to have him give a talk on the chiral density wave in topological semimetal European aluminum 4 that he discovered very recently. Yeah, okay, yeah, thank you, Miao.
Yeah, thank you, Punchen, for the kind introduction. Also, very happy to be here again to talk about our work on or our understanding of chiral density waves. So let me see if I can turn on the laser. Okay. So chirality is sort of a ubiquitous concept. It's from a Greek word, means handness. So it's sort of a phenomena that being found from all length scales, as small as subatomic level, or people know about the DNA, which is a chiral molecule, and we have chiral crystals as well. And even if you go to the galaxy level, then you often see chiral galaxy. So this is really fundamental phenomena in nature. If we talk about so talk about condensed matter physics, chirality is also a very interesting concept. So it's back to 1980s. Haldane proposed his famous model creating a loop current to stabilize the quantum anomalous Hall effect. And in 90s, Chandra Varma proposed the loop current for the cuprate to understand the pseudo-gap phase. And more recently, people start talk about in Kagami metals. And similarly, chirality can exist in quantum spin liquid, or combine chirality with superconductivity or spin texture. So basically what I'm trying to see is that chirality is a very interesting idea if we combine that can lead to discoveries. So for this talk, I want to focus on density waves, chiral density waves. So basically, density wave is a state of matter that breaks the translational symmetry of the underlying lattice. We can talk about charge density wave. Basically means the charge density modulation in real space breaks the underlying lattice translational symmetry. We can also talk about spin density wave, meaning the spin density distribution in real space breaks the translational symmetry of the lattice. We can also combine CDW, SDW, and superconductivity. Then we can have a pair density wave, which has attracted significant interest in the community in past few years. For this talk, I want to focus on CDW and SDW, and I hope in near future that we can discuss a little bit our recent work on pair density wave as well. But nevertheless, today's topic is CDW and SDW. So the material I want to focus today is European aluminum 4. This William Meyer that grew a beautiful sample for us. So here shows the crystal structure of European aluminum 4. The structure, I think many of you already know, is same as the famous iron-based superconductor and heavy fermion superconductor. If you look at the band structure of this material, it's actually a semi-Dirac semimetal. So when I say semi-Dirac, it means the band dispersion is linear along one direction and the parabolic in the plane that's perpendicular to that direction. So more specifically for this material, along the KZ direction shown here, it's a linear Dirac cone. But if you look at dispersion in the AB plane, it's a form a parabolic touching. So this is what I mean by semi-Dirac metal. But of course, we are interested in this material is not because this, I think not only because of this topological electronic band structure, but more related to its fruitful phase diagram. Here I show the low temperature phase diagram. The vertical axis is the magnetic field. The horizontal axis is the temperature. You see there's a lot of phase, not too surprised for rare earth metal, but part of the interest is because there's a large region that people believe it forms a skyrmion. The skyrmion is kind of small, and people are debating what drives the skyrmion, maybe RCQY or whatever the mechanism. If we focus on the zero field, and here's the phase diagram, and if you zoom out the temperature axis, you see CDW emerge around 140 Kelvin, about 1 order magnitude higher than the spin density wave or skyrmion phase. So basically, in this material, it features spin and the charge density wave and the topological spin texture and topological electronic band structure. That's the reason why we are interested in this material. As I just said, today I want to focus on the chiral CDW and the spontaneous chirality flipping in this material. Because the CDW appears at a higher temperature, I want to start from the chiral density wave. So our paper is recently posted on arXiv. If you are interested in more details, you can always go there and check all the details. So before we discuss about chiral CDW, I think it should define what do we mean when we say chiral CDW, because it's not commonly seen in materials. So I think it's a good idea to start to look at what the chiral spin order looks like and get some insight. So here I sketch a helical spin order. So you see spin orientation is winding along an axis. So that's form a chiral spin texture. In order to have this type of spin density wave, you either break the inversion symmetry to allow a DM interaction to give you chiral spin texture, or you can have like competing magnetic interactions such as RCQY that I'm drawing here. Then if you apply magnetic field, you can select one chiral spin order over the other. With this, basically, I think it's quite clear. In order to have a chiral density wave, first of all, you need a vector order parameter. Secondly, you want it transverse so that you can define your chirality. And then finally, to have this order, you definitely need to break some symmetry, such as inversion symmetry or time reversal symmetry. But that basically gives a puzzle because charge density is a scalar physical quantity. So actually, it makes no sense to say chiral density charge density wave. So in order to talk about chiral charge density wave, what we really mean here is we need to consider not only the charge density, but we also need to consider the lattice distortion, because the lattice distortion is a vector physical quantity. When you put them together, then we can define a chiral CDW. So that's what I mean about chiral CDW. So now the next question is, how do we realize a CDW that has transverse lattice distortion? So before I have that, let's just again review the fundamentals of a charge density wave in 1D. So here I just sketch the famous Peirce transition. So actually, quite interestingly, for the Peirce model, he actually only considered the coupling between electron and the longitudinal acoustic phonons. The reason is because for a single atom in one unit cell, and the main energy cost is from the volume change. So if you go back and check, then you will find for the electron phonon coupling, the longitudinal acoustic phonon always dominates. And once you have a Fermi surface at a high filling, then you favor a Peirce transition, and you open a gap at the Fermi level. So that's the story that everybody know. So the question is, how do we create a transverse lattice distortion? Turns out it's quite simple. Now, in real materials, we don't necessarily have a isotropic s-wave electron, s-orbital electron. We can have electron conduction electron with p orbitals. So once you have a very anisotropic orbital, then you can imagine the transverse lattice distortion can affect your conducting electron more. Then in this case, you're going to have a transverse charge density wave. So as experimentalists, we will always want to know how do we distinguish like longitudinal pairs transition, transverse pairs transition. Is there any physical measurable quantity that we can really talk about that? So here shows how do we distinguish the longitudinal or transverse. On the left, I show the cone anomaly that only appears on the longitudinal acoustic phonons. And consequently, you will have a longitudinal pairs transition. But for the transverse pairs transition, you would expect the longitudinal phonon doesn't show much change as you're cooling down, but instead, the transverse acoustic phonon should show a cone anomaly, and the transverse acoustic phonon will condense, gives you the transverse pairs transition. Once you can experimentally establish transverse pairs transition, then that opens up a lot of new possibilities. For example, if you imagine a transverse lattice displacement showing here, so and if you look along the z-axis, then you would expect the rotational symmetry of your material is broken by the transverse CDW. That will end up a C2 charge density wave or C2 transverse pairs transition. On the other hand, you can also have a lattice distortion sort of a chiral. In this case, you can preserve the translational symmetry, but you break inversion symmetry, and you will realize the chiral CDW. So really, the key point is you first need to realize the transverse pairs transition, then you have all kinds of different charge density wave patterns. Of course, we can talk about why the C2 versus the chiral density wave is more energetically favorable. The lattice energy always dominant, but we can also think about the condensation energy of the Fermi surface. Here you can imagine for a C2 charge density wave, your CDW gap would be highly anisotropic versus a isotropic CDW gap that's for this chiral CDW. So here I want to jump onto the material and show you in europium aluminum 4, it really forms a transverse CDW. So on the left panel, I show you the X-ray diffraction data as a function of the temperature, and we can clearly observe the CDW superlattice peak around 140 Kelvin. So interestingly, if you do a L scan of at the CDW peak and change the temperature, so we don't see the expected critical dynamics, meaning the peak width doesn't change with temperature. What you see is only the peak position change, which is what you expected for an incommensurate CDW. When you're cooling down, the commensurate energy will dominate the condensation energy, and then you will change from incommensurate wave vector to commensurate wave vector. So this is fully expected. But if you look at the X-ray scan in the AB plane, then you start to see dramatic change where at the low temperature, the peak width is very, very narrow. I think it's resolution limited. But near the transition temperature, the peak becomes significantly broadened. So that means the critical dynamics is really from the transverse lattice displacement. We can do a bit better by imaging the lattice distortion using TEM. So Miao et al. Help us to check the image of the europium aluminum 4. Here's the TEM image and TEM cut at room temperature. And once you're cooling down, you can start to see the displacement, and they can confirm the lattice displacement is coming from the aluminum atoms that is transverse, that perpendicular to the CDW propagation wave vectors. Finally, we want to really justify it's a transverse by measure the phonon dynamics. So here shows the transverse acoustic phonon dispersion at room temperature, and the panel B shows the longitudinal acoustic phonon dispersion at the room temperature. And this panel shows the dispersion slightly above the CDW transition temperature, and we can observe the softening of the transverse phonon, but the longitudinal phonon doesn't really change. Here shows the IXS spectrum that we can clearly see the softening of the transverse acoustic phonon, and there's not much change on the longitudinal acoustic phonon. So these panels summarize what we observed. Indeed, the longitudinal acoustic phonon doesn't respond to the CDW, but the transverse acoustic phonon show a cone anomaly. If you remember what I just showed you before for the schematics, so these observations really prove for europium aluminum 4, the CDW is a transverse Pierce transition. Then we can ask what's the role, what's the drivers of the transverse Pierce transition. So we ask Xi Dai and his student Kai Fa to help us calculate the charge stability. So here shows the DFT calculated band structure. First, we confirmed near the Fermi level, the electron mainly has px and pay orbital, as I showed you before. And we can calculate the charge stability along the gamma z direction, which is the CDW wave vector direction, and you do observe a charge stability peak at the CDW wave vector. And we can also calculate the electron phonon coupling and the phonon dispersion at the finite temperature and the zero temperature. Again, you find the phonon softening induced by transverse electron phonon interaction. I have to mention that this calculation was done for strontium aluminum 4 because europium is sort of heavy Fe electron element. To properly treat it may have a problem, but still we also performed a measurement for strontium aluminum 4 that we confirmed the CDW, which is exactly at the DFT calculated wave vectors. Now, I think having the transverse Pierce transition in europium aluminum 4 established, then we can ask whether the CDW is a chiral or a chiral. One way to distinguish it, we can check the rotational symmetry in the CDW phase. If it's a C2, it could be very likely a C2 or a pneumatic charge density wave. If it's a C4, then there's a possibility to host a chiral CDW. So here I just sketched two possibilities that give you C2 crystal structure, and the C and the D shows the expected fundamental Bragg peak splitting. So if you have, for example, IMM, lattice point group, a space group, meaning the atomic displacement is along A or B, then you should see lattice displacement, Bragg peak displacement splitting showing C. If you have a lattice displacement along the diagonal direction, then you should expect Bragg peak splitting schematic showing D. So we did very careful Bragg peak measurement at the 90-degree related fundamental Bragg peaks, and through the transition. Based on our experimental resolution, you can estimate the upper limit of the lattice displacement, which is around less than 2 picometer. And if you calculate the Heisenberg uncertainty principle for the lattice vibration, it's about 3 picometer. So what I'm saying here basically the splitting already make no sense at this temperature. So therefore, we believe at this temperature, there's no four-fold symmetry breaking. Indeed, if you really cooling down, you see the four-fold rotational symmetry breaking around 12 Kelvin. So that's again a confirm that below the CDW transition temperature at 140, there's no four-fold rotational symmetry breaking. So this is low temperature symmetry breaking kind of confirm or consistent with thermodynamic measurements and the neutral measurement. So based on this study, we believe we can rule out the nematic charge density wave, and we're going to have a C4 rotational preserved charge density wave in europium aluminum 4. And then we want to ask a little bit more, exactly like what the point group is. Then we ask Liu Yan from Michigan to help us check the second harmonic generation. So here is the azimuthal dependence optical measurements, and here is a fitting of these patterns. Again, we can confirm that throughout the CDW transition, there's no C4 rotational symmetry breaking. What is really interesting is that below the CDW, the pattern rotated away from the high symmetry directions. What that means is that below the CDW, all mirrors, all in-plane mirrors are broken. And this is not only observed in one sample, we can confirm in multiple different samples. That means below the CDW, there's no mirror symmetry in the system. So based on all the measurements and based on the subgroup of the high temperature phase, we basically conclude in the europium aluminum 4 is either ferro-orbital charge density wave or chiral CDW. So the difference between these two is basically the ferro-orbital, you're going to have left-handed chiral CDW and the right-handed chiral CDW. So basically, we cannot distinguish the domain or the ferro-orbital CDW. But nevertheless, all these measurements suggest that there is a chiral lattice distortion in the CDW phase in europium aluminum 4. So that's basically a conclusion about our understanding of the CDW phase in the europium aluminum 4.
So let me ask you, Miao,
yes.
So what happens at 14K in her measurement?
14K.
Yeah, I mean when you see the chiral charge order, I mean when you chiral spin SDW. I mean she only had the data actually down to 80K, right? Yeah, what happens here?
At the 13K? Yeah. So at here, the four-fold rotational symmetry is broken, and I will discuss in more details for soon. And basically, the double Q spin density wave becomes a single Q helical spin density wave.
Okay, thank you.
Yeah, sure. All right. So now I'm going to focus on the spin density wave at the low temperature. So I just want to remind you the zero field phase diagram. Indeed, around 15 or 16 Kelvin, the system form a double Q spin density wave with a wave vector around Q11 direction. And if you go through T2, then the spin slightly canted along to the z-axis. So, and you're going to have a new superlattice peak along H or K, but they still double Q spin density wave. Below 12 Kelvin, the four-fold rotational symmetry is broken, and you form a single Q helical spin density wave. And then if you further cooling around 11 Kelvin, then you're going to have another transition from a single Q helical to another single Q helical, but the wave vector changes slightly. So our initial interest for this study is why the system want to change the Q, why it cannot stay just at this Q. So that's the real motivation for the magnetic study. In order to study the magnetic phase, the technique we use is resonant X-ray scattering, magnetic scattering. So here is the geometry. To do this, you need to tune your photon energy to match the energy difference between your core electron and the unoccupied state. Once into that phase, you can be sensitive to magnetic structures. Here, I just show you the resonance fluorescence scan, and we can observe quite clear European L-edge resonance. So once you are on the resonant condition, your X-ray cross-section can write in this form. The first term here is kind of an effective Thomson scattering cross-section. The second and third is related to the magnetic scattering. The third term is generally very, very weak. You can consider as a higher order correction. So most of the time when we talk about resonant X-ray magnetic scattering, we only focus on this term. And for this particular situation, since we have a single Q helical spin density wave, then we can calculate the circular dichroism analytically. I will skip all the detailed calculation. Basically, for single Q helical spin density wave, your circular dichroism is proportional to tau and chi. Here, chi is your chirality. Tau is a number that's related to your wave vector. So let me explain here a little bit more. Assume you have a single domain helical spin density wave. You're going to see circular dichroism. But if you look at the positive Q and check your circular dichroism, it will be negative. And once you go to the negative CW wave vector, it will be positive. So the sign would be different. It's naturally arise from this formula. So this would be a key signature to use resonant X-ray magnetic scattering to distinguish a helical spin density wave. So now we can move on to the experimental data. We first test our experimental technique on the structural Bragg peak. Not surprised there's no circular dichroism at all because it's a structural Bragg peak. Once you move to the magnetic superlattice peak, now you can see the positive circular dichroism on the positive Q, negative circular dichroism on negative Q. That basically means at 9 Kelvin, the magnetic domain has positive chirality. But once you cross the phase transition from a single Q to another single Q helical spin density wave, you see the circular dichroism flip sign. So now at a negative Q, it's become positive, positive circular dichroism. For positive Q, it becomes negative circular dichroism. So that means the chirality, even where stay on the same spot, is changed from positive to negative. We can further increase temperature to the achiral double Q spin density wave phase. As expected, there's no circular dichroism at all. And we can also check the energy dependence. And here we only observe the circular dichroism on resonance. That's once again confirm the circular dichroism coming from the magnetic order itself. Quite interestingly, so we can ask, what happens if we warm up and cool down? Does the chirality remain the same or the chirality would be different? So here we show the hysteresis scan. We start changing temperature even above all the magnetic transition temperature and cool back down. So what happens is all the chirality always remains the same. Even we warm up above all the magnetic transition temperature, that means there's a pinning center that exists above all the magnetic transition temperature. So that's basically, we ask ourselves why it happens. So a naive expectation one may expect is because there's a higher temperature CDW, maybe the CDW gives the pinning center in that case, we expect the CDW going to be strongly coupled with the SDW. Indeed, this is the case. Here, A and B shows the magnetic or SDW wave vector as a function of temperature. It changes quite a bit when you're cooling down. But what is really surprised is that for the CDW wave vector has a strong response whenever we enter into a new spin density wave phase. When I say surprise, I mean the CDW at the low temperature already commensurate with the lattice. But once you enter a spin density wave phase, the CDW move away from the commensurate phase to an incommensurate phase. So that's quite surprising. Another surprising comes from the CDW propagation wave vector, as I'm showing here, is perpendicular to the spin density wave. So even though they are perpendicular to each other, they still show quite strong coupling. So with all this experimental data, then we start to ask our theoretical collaborators, say, what drives the magnetic phase, and how do we explain the chirality flipping in the system? So Juba and Stefan performed the first principle calculation. What they find is that if you calculate the RCQY interaction, it turns out the helical spin density wave indeed is a ground state for this particular material, and they can even estimate the transition temperature, which about 16 or 20 Kelvin, very close to experimental value. Even the peak in the momentum space is quite consistent or quite close with the experimental measured value. So basically, these calculations confirm that in this material, the delocalized RCQY interaction is dominant or determines the magnetic texture of europium aluminum 4. Since the delocalized interaction plays an important role, then we bring this information to Yang and Christian and ask, how do we understand the chirality flipping? So based on the fact that one, across the transition, we have a chirality flipping, and we also have the wave vector change. And then they propose that because the delocalized interaction nature, maybe the DM interaction is also momentum dependent. Indeed, if you consider the next nearest neighbor interactions, then you will find the DM interaction will flip the sign in real space. And we believe their competition between these two vectors might drive this spontaneous chirality flipping. So now I think we can summarize what we have been observed. So basically, I think we have strong experimental evidence to establish the transverse Pierce transition in europium aluminum 4. We have quite strong evidence supporting a chiral lattice distortion in the CDW phase. And we're quite sure in this system, the spin, orbital, lattice, and the charge degree of freedom are strongly intertwined. And looking to the future, we believe this knowledge may help us understand the origin of nanometric skyrmions. And another interesting observation for this material is that on the europium aluminum side, the CDW is C4. But if you dope like 50% gallium, then the CDW is C2. So we're interested how the CDW changed from four-fold symmetric to two-fold symmetric. And also, we are actively pursuing directly imaging the CDW and the SDW domain using resonant elastic X-ray scattering. Then we might be able to comment more on the nature of chirality flipping and the chiral spin density wave. And with that, I think I can stop here and happy to take your questions. Thank you.
Yeah, it's a very, very nice talk.
Yes.
Yeah, so I guess, I mean, I don't understand, I guess, I mean, what do you mean actually by chiral charge order? You mean it's a single domain that the atoms are actually rotating transversely along?
Yes. So let me go back to to the cartoon. No, actually this one. So if we have, assuming these vectors pointing to the indicating the lattice displacement direction.
Mm-hmm.
So you can imagine this is the c-axis. Let's say aluminum one layer displace go up, and the other layer have a 90-degree rotation, and then goes down, and another 90-degree rotation. So the lattice distortion forms a chiral structure. So that's what I mean, chiral CDW. So we have to consider the lattice distortion and the charge density wave in order to make it sort of a chiral.
I see. But lattice itself has no vector. It's not a vector, right? I mean, how can it be? I mean, I guess your left and right turning, it should be no difference, right?
So you can imagine there's a lattice distortion could have direction. For example, if you imagine a chain, then relative to its high temperature position, it can move up or move down or move left or move right. So then that's basically a direction that we can trace.
I see. I see. So you're basically saying that I mean, but then you say this is highly coupled with the spin.
It doesn't couple to spin, so it just the lattice distortion. So how about think about this: the tellurium single crystal.
Mm-hmm.
So tellurium is well known as a chiral structure, right? So basically, the atom form a triangle, but if you look from top, but if you look from side, it's kind of a chirally go up. So you can imagine at a very high temperature, it's just a 1D string. And then as you cooling down, then it's displaced from a chiral displacement. So you can imagine that way.
So in this case, it's purely aluminum that does that.
It's purely aluminum, yes. There's no coupling with.
I thought there's a strong coupling. I mean, I saw in the later talk you said there's also a couple with a spin.
Yeah, that's right. That's true. That's true. So once we went to the lower temperature, when the magnetic phase pop up, they become strongly coupled. And exactly how they coupled, we don't know yet. But based on the data, we know it must be a very strong coupling.
I see. So the chiral CDW order occurs at 140 K, higher temperature.
Yes.
And
yes.
then it only couples to spin at lower temperature.
Yes, I think because the spin can only order at a lower temperature. It's a rare earth. So it's not surprising.
So when the spin order, chirality changes direction, what happened to your charge CDW chiral order?
That's a very good question, and we are looking into that. It kind of turns out to be not easy experiment, but we're trying to push.
Oh, I guess you have to do X-ray below 10K. That's quite hard. Yeah.
Also, we also want to trace the chirality of the CDW. So this is a little bit complicated, but we're trying to do that.
I see. It's actually quite. It's amazing. I mean, like I asked you earlier. I mean, I still don't understand what changes inversion symmetry, but let's leave that aside. Yeah. Okay.
Yeah. Mm-hmm. We don't fully understand the microscopic driving force. Mm-hmm. Initially, I thought so. If you starting from the spin pairs, or not spin, I'm sorry, the transverse pairs transition picture. Shidai had a paper say if there's a chiral phonon that's gonna and topological band structure, then you have to preserve the pseudo-angular momentum, and then you might be able to stabilize chiral density wave. I don't know if that's true or not, but it could be a possible scenario.
Okay, very interesting. Okay, Pavel, you have a question?
Can you go to the slide where you compared the two Bragg peaks that are related by C4 symmetry?
Yeah.
For the CDW, yeah. Yes, exactly. So the width of those looks different at all temperatures, or is it just a different scale? Like just in the figures, the left and the right, the width.
Yeah, I think that's the so the Q resolution for X-ray is not always the same. It depends a little bit on your experimental geometry. So I think throughout the temperature is sort of resolution limited. So it's just the resolution.
the second question is whether there are some transport signatures of the CDW transition. So if it was some kind of C4 break-in, maybe you expect some anisotropy. And with this chiral, I wonder if there is some magnetochiral current when you apply, current along the C-axis, so you generate magnetization, something like that.
That's excellent question. We're thinking to do the C-axis transport measurement as well. I'll keep you updated. I think that's great suggestion. Yes.
Is it a highly 2D material or not?
Sorry?
2D. Is it highly two-dimensional material?
No, you can cleave it, but I don't think it's 2D.
It has the same crystal structure as iron-based superconductor. I mean, except
Yeah.
You replace I guess the iron with europium, right? I mean, yeah.
Yes.
Europium is actually internal. Yeah. Has actually a BCC. I mean, europium itself has a BCC structure.
Yeah.
Okay.
Yeah. So if you cleave, I think you're gonna expose the europium layer around here. It's not very 2D. We actually have DFT calculation. Well, actually, you do see. Let me see. Yeah, here's the DFT calculation. It forms a direct point, so it's highly dispersive along the axis.
So I mean, have you done measurement on, if you dope it with a gallium, have you see whether this chiral CW changes?
Yeah, we feed two beam time. The CW transition temperature showing quite interesting behavior. So it first goes down and then goes up.
I see, but I mean, it's still chiral. I mean, once you dope it.
We haven't checked the chirality yet, but I think for low doping, yes. But for high doping, no, for sure.
For low doping, what is your low doping?
I think we checked like 10% gallium doped sample. It's still C4.
I see. That's very interesting. Okay.
Yeah.
Okay.
But we need to check a little bit more. But this is an ongoing project, and we do interested to see how the doping gonna change the chiral to C2.
I mean, it'd be very interesting to know, what the chiral, your chiral CDW does, right? Below the chiral spin order. I mean, to see whether there's actually direct coupling or not. Yeah.
Yeah. I mean, so another kind of possibly interesting thing is, like, for example, at the zero field, below 12 Kelvin, the structure is C2. But if you apply small magnetic field, not small, maybe 1 or 2 Tesla magnetic field, the structure-wise change from C2 to C4 again.
Yeah, you see skirmions. Yeah, I mean, that's what I'm
so
you actually see skirmions. Yeah.
So we have experiment trying to test if we can use resonant X-ray scattering to directly characterize the chirality of a CDW. So far, all the evidence sort of indirect. We don't have the magnetic X-ray scattering type of measurement to directly say, oh, it must be chiral CW. So all the measurement based on symmetry arguments, but we are doing soft X-ray resonant elastic X-ray scattering with the hope we can directly determine the chirality of the CDW.
I see.
And then I think we can trace more carefully how the chiral spin density wave affect the chiral CDW.
Okay.
Yeah.
Okay, maybe chiral CDW, form the basis for chiral, SDW. I mean, that's sort of a form of template. But then I'm still surprised, why is it suddenly changes, 100% changes the direction, as a function of temperature. That's actually quite amazing. Yeah.
Right.
I understand that. Yeah. Okay.
Yeah.
Yeah. Okay. Are there any other questions for who? Okay, great. Yeah. If not, I mean, thank you very much.
Yeah. Thank you for your invitation.
Yeah. Okay.